A very good morning to everyone. My name is Swati and I'm an applications engineer at NI Singapore. This webcast is the last one in the Embedded Technology webcast series, and thank you all for joining me here today. As engineers, we face so many challenges on a daily basis, building systems using disparate tools, integrating existing equipment with new hardware, and adapting to the changing requirements over time. We have fewer resources and less time to get to solutions. The complexity of dealing with these everyday challenges can sometimes make us lose sight of the real impact that engineers have on the society. Engineers increase wealth by saving companies time and money and improve the quality of life and the safety of all of us. That impact is our value, and in fact, that is why we do our jobs. When the pain of tools and technology distract us from the engineering we are supposed to be working on, now that's a serious problem. At NI, our mission is to equip engineers and scientists with systems that accelerate productivity, innovation, and discovery so that they can realize the impact that great engineering and science can have on our world. NI has a strong track record of sustainable growth and profitability because we are managed for the long term. We believe that the best way to serve our customers is to ensure a successful, stable company which our customers can rely on products that will be of consistent quality over time and provide customer service for the decades that the products will be used. So what sets a National Instruments approach apart from other traditional approaches in embedded system design? It is that we offer a platform-based approach. This platform combines a full-featured, highly productive, a graphical programming environment with customizable off-the-shelf hardware. When you combine the flexibility of hardware and software into an integrated platform, engineers can focus more on solving the challenges of industries rather than worrying about the communication between the hardware components or developing the basic software components or designing a user interface from the ground up. In addition to the flexibility of this platform, it also combines the ability to implement custom algorithms, high-speed control and processing, and world-class analog and digital I/O into a single system using all off-the-shelf products. Finally, this platform is stringently built and tested with the highest quality, which allows you to deploy reliable systems that last even in harshest environments. We call this platform-based approach graphical system design. Graphical system design is about using intuitive graphical software to define hardware functionality. This translation is made possible by the LabVIEW platform, housing multiple ways of describing systems that can automatically deploy to multiple processing and I/O platforms. This accelerates the development of any system that needs measurement and control in tests, monitoring, embedded, control, or any combination of these applications. And as you can see, the results were astounding. Not only NI customers complete more projects on time, but they are doing it in less time with fewer resources than those who are following the traditional approaches. This is made possible by using the platform-based approach. Graphical system design provides quality products and the confidence to innovate while getting your project done in very less time. Now let's take a look at the landscape of processing targets. This shows a typical range of targets, and FPGAs have reached roughly $5 range in high volume, which makes them attractive not only for proof of concept research prototypes, but also for much more like mass-produced converters and motor drives. Below this range, you typically see custom application-specific integrated circuits, or called ASICs in short, and specialized low-cost microcontrollers and microprocessors. And that's what dominates the market today at very high power levels. The challenge with those is that the non-recurring engineering cost to create one of them tends to be quite high, particularly for the ASICs. So the increasing adoption of the FPGA controllers is raising considerable interest in finding the most efficient and appropriate development process for power electronic control systems, especially given that the FPGA embedded system development represents a significant paradigm shift compared to the development for microprocessors, microcontrollers, and DSPs. So let's look into what's inside FPGA technology and how they work under the hood. An FPGA is a device that contains a matrix of reconfigurable gate array logic circuitry. When an FPGA is configured, it's quite different from programming a processor. As you all know, processors are designed to offer high flexibility and enable you to implement very complex applications by providing different layers of abstraction. However, if you're implementing a very specific task that requires extremely high performance or reliability, your task will be limited. But if you move the calculation to hardware, you can achieve very high performance or high reliability and a response time on the order of nanoseconds. This is what an FPGA enables us to do. The internal circuitry in an FPGA is connected in a way that it connects the hardware implementation of the software application. Also, FPGAs are truly parallel in nature, so different processing operations do not have to compete for the same resources. As a result, the performance of one part of the application is not affected when additional processing or logic is added. And we implement this in the LabVIEW RIO architecture. RIO stands for Reconfigurable Input and Output and refers to LabVIEW's ability to program FPGAs through graphical code. This architecture involves an FPGA that is directly connected to various analog or digital IOs, which gives us extremely fast and deterministic loop rates and the ability to implement custom logic and protocols. The FPGA exchanges data and commands with real-time or PC-based processors, which is also running LabVIEW, allowing us to seamlessly manage data and integrate a user interface. Graphical system design is not limited to traditional CPUs or microprocessors, but also can be seamlessly extended to harness the flexibility, speed, and reliability of FPGAs. And now, moving on to the key trends that impact the embedded system design. First is reconfigurable heterogeneous architectures. When faster CPU cores fall short, embedded system designers are combining heterogeneous processing elements like reconfigurable FPGAs with the CPU cores to meet their application needs. Second is the democratization of embedded system design teams. Many design teams are abandoning larger, specialized teams for smaller groups, which are more focused on translating the domain expertise into realized innovation. Third, the total economic profitability. More companies are adopting a comprehensive approach that considers not only cost-benefit analysis, but also factors like flexibility and risk. Fourth is the embedded vision. Technologies originally used in high-volume consumer devices is now powering a new generation of intelligent embedded system devices. Fifth is a digital energy revolution. Digital technologies are changing the way we manipulate, move, control, and store energy. And now we'll be taking a closer look into this aspect here on. Power electronic technologies have been advancing very significantly in the last decades. And with technologies going digital, for example, the transformation from printed books to digital books, they bring us a lot of new benefits. And the good news is that now energy itself is in the midst of digital revolution. We are entering this era, or I would say we are already in this era of digital electricity. We can digitally convert, control, manipulate, and even store energy. Abundant processing power, high-efficiency power transistors, and graphical system design tools are changing the way we manipulate, move, and store energy. Here are some of the top NI digital energy applications which were developed for microgrids, for power transmission and generation units, for transportation like electric and hybrid trains and vehicles, and also for industrial applications where almost 60% of the electricity is used. What's driving the digital energy revolution? Firstly is Moore's law, the exponential increase in performance per dollar as well as the number of transistors in embedded processing technologies. This concept actually applies to other technologies like high efficiency power electronics and also lower cost renewables. With increasing popularity of ubiquitous networking, it is expected that the requirements of a digital energy grid can be handled using any device in any location and in any format. Another area is the need for accurate real-time simulation. This enables us to digitally simulate and design the advanced control systems needed for digital energy revolution, and it is a critical piece of the puzzle. In this webcast, we shall dive deep into what NI offers for accurate real-time simulation. National Instruments R&D is making investments to provide a new system-level design methodology and platform for FPGA-based power electronics control. We want to understand and eliminate the issues that reduce the productivity of embedded design teams. At the highest level, the goal here is to create a world in which energy becomes just a software problem, like looking for the right algorithms to efficiently convert, control, transfer, and store the energy. That's what the digital energy revolution makes possible. How will we know that it has happened? We can call it a digital energy technology if the system is digitized and digitally controlled, networked, field reconfigurable, modeled and simulated, and improving exponentially in performance per dollar each year. What grand challenges of engineering will the digital energy revolution help us address? For now, one thing is clear. These technologies are rapidly increasing in performance and falling in price, and they lie at the heart of renewable energy, smart grid, and electric vehicle systems. Here are the power electronics design goals and trade-offs. In the power electronics space, we are talking about trying to increase the energy efficiencies of the designs by at least as little as 0.1%, which actually involves months of engineering work. Here are the trade-offs and constraints that people have to deal with when they are designing these systems. And the engineers have been asking for is a tool chain. NI proposes the graphical system design approach to develop one such tool chain. This figure clarifies the differences in design flow between the traditional methodology and the graphical system design methodology. The salient feature of our approach is that high-level graphical implementation code for the FPGA rather than a high-level software model is developed in the simulation context and then automatically synthesized to FPGA hardware. By automatically synthesizing the implementation code, which is inclusive of the interfaces to analog and digital I/O, the need for any knowledge of register-level FPGA programming languages like VHDL or Verilog is eliminated. The approach is also bidirectional. Bidirectionality implies that the same implementation code is used in both simulation and deployment contexts, such that the changes made in their context are automatically and necessarily reflected in both. In this way, a single instance of the implementation code can be edited and evolved continuously during the development. Furthermore, testing of the implementation code in the simulation context can be fully automated to enable comprehensive validation and verification against formal design requirements. By contrast, in the traditional methodology, sometimes called as a model-based design, the simulation environment is used to develop the models. Then a multi-step process is used to convert the model from the continuous time domain to discrete domain, from floating point math to fixed point math, and from system level code to automatically generate register level code. This development methodology is also unidirectional. So let's take a look into the major investments underway at National Instruments R&D to advance what we call the graphical system design platform to satisfy the needs and provide a comprehensive new tool chain for this era of digital electricity. Our vision is to complete the redesign for power electronics, and we are making major investments along each steps of this to provide new tools that we hope will enable significant improvements in design, prototyping, and deployment process to get new products and technologies to market. And these are based on digital modern power electronics control systems. It starts with the first stage of design. There are graphical co-simulation tools that link together with multi-sim SPICE environment and the LabVIEW FPGA programming environment. Now these are both very mature technologies, but what's been missing is a high fidelity link that lets you actually write your FPGA code onto the desktop, simulate it against a high fidelity simulation of power electronic systems, and get accurate results. It's a tricky problem to solve because you have a lot of transients and harmonics and other characteristics in power electronic systems. So we made some advances here to create a variable time step co-simulation interface between the tools. And that's really a game changer because it means that either the FPGA side in LabVIEW or the multisim circuit simulator can ask for a smaller time step. So you'll notice when you run these simulations that it actually slows down if the power electronic circuit starts resonating or oscillating to capture accurately the dynamics of that interaction between the control system and the power electronic system. And that's critical because traditionally these co-simulation tools, and there's a lot in the market, use fixed time step. So the only way to know if your results are accurate is to use a smaller time step and compare that to a larger time step. And the problem is that the actual time step you need varies widely during the simulation. For example, if you're simulating the control system for a wind turbine generator or an electric motor generator, when the motor or generator is running at full speed, you may be able to get away with very large time steps because the system is pretty static. But that's a different story when you reverse the H bridge and apply minus supply voltage across the motor and it's already spinning with a lot of back EMF. So we have released these new tools which embrace the reality that you need to vary the time step to accurately capture the coupled dynamics between the control system and the plant. The next thing is engineers need to have a platform which they can rapidly prototype their control systems. And this is a diagram showing the MathWorks Sim Power Systems, which is a popular tool in academics for simulating power systems. We can run those models in this multi-core compact Rio system, which has a dual-core i7 heavy-duty floating point processing capabilities. We can run them on the order of 20 kHz to 40 kHz. So we finally have an embedded system that has this rugged form factor and the type of industrial I/O modules that you would want for power electronics that have the horsepower to run these modules quite quickly. We can run these models on the order of 40 kHz on the processor. That's useful because you can prototype your algorithms. You still run into the problem that processors typically hit the wall, regardless of how high end you go, at about 100 kHz. And that's just due to bus latencies, regardless of how much processing power you have. And that's actually one of the big pressures pushing people towards FPGA-based control. And next is the NI General Purpose Inverter Control Platform, or called as GPIC. The idea here is to have a very universal, very general purpose platform for controlling AC to DC converters and DC to AC inverters that has all the right I/O. It's in a very cost-effective form factor, and it has the greatest technologies from Xilinx and Freescale. At the heart of the system is the FPGA, which is really a game-changing technology for power electronics control. The next piece is a real-time simulation. Like mentioned before, the 100 kHz limitation that processors run into, and this is a real challenge because even with a big GPU or multi-core processing system with lots of computing power, you have these bus latency issues. And for power electronic systems, you really need to simulate above 1 MHz rates, and it's extremely hard to get above 100 kHz on a processor-based system. So we are making heavy investments to make open, off-the-shelf tools for running high-fidelity simulation models of power electronic systems on the FPGA. In fact, it's the same tool chain you can use to program your FPGA-based control system that you can use to develop these real-time simulators as well. And what you can see on the screen there is now a GMAC finite element analysis model running at megahertz speed on a high-end FPGA called FlexRio. It takes a lot of FPGA processing horsepower to run these models, but it's extremely high fidelity, and that's really a game changer. Now, there is a big problem in testing power electronic systems. For example, if you're developing an electric motor control system for an electric vehicle, a traditional dynamometer doesn't really work that well for testing it. And the problem is that the dynamometer is a mechanical system, is effectively a big low-pass filter, and the 3 dB roll-off on those are typically 10 Hz to 100 Hz. But a lot of dynamics, as you know, in these motor control systems are up in the kilohertz speeds. And so what you see on the right is an alternative to a dynamometer, an electric motor emulator. It's basically an advanced inverter that runs at very high switching frequencies. And the purpose of it is to run a real-time simulation of the power system and let you dynamically test the inverter under full power so that you can exercise the inverter. And it has frequency response in the kilohertz speeds. This kind of real-time simulation is absolutely required to have comprehensive validation and verification of the embedded control system, and it is a standard practice to use this kind of HIL simulators. The problem is it's been very expensive or difficult or even impossible to do this for power electronics. But now these tools change the rules. You can do these simulations based on just a generic state space model that runs in the FPGA. And then finally, we have the issue of how to physically test those power systems, especially in the megawatt range. It is pretty challenging. You don't just walk up and hook up a regular scope or digital multimeter to grid-tied power systems. And so, we have partners like Bloomy Energy and other companies around the world that are making specific investments to build on top of the NI technologies to have really good testing systems that are designed for kilowatt to megawatt power electronic testings, and hence completes a design V. Now, let us discuss the problems with embedded design. One problem is that the transistor count is doubling, which means that the number of pins on the device is also increasing rapidly. And we've seen this transition from the DIP packaging to the modern packages like ball grid array, which means every pin on the device has many adjacent pins. So you have a lot of issues with EMC, crosstalk and signal integrity. And trying to do your PCB layout for these modern VGA packaged devices is really challenging. For National Instruments design engineers, they are very experienced and have software tools to do these layouts correctly and with high reliability. It's increasingly difficult for small companies to do these kind of layouts, and so that's creating a lot of interest in having off-the-shelf boards that have the processor, DSP and FPGA on them. Engineers are still doing some custom design, but for the processing part, they'll buy as an off-the-shelf board that has been pre-validated and is reliable. It's got software tools that make it work, and so on. And so, this is putting a lot more pressure to have off-the-shelf boards like single board Rio that have these modern devices on board. And also, to have companies that keep you up to date on the very latest chipsets and technologies like the way National Instruments works with Xilinx and Freescale and Intel to get their devices early and then release them as quickly as possible so that our customers can use them and go to market with their embedded systems. This is really moving people to want to leverage COTS technology more and more. This has really been the National Instruments model from the beginning, to provide the latest, most state-of-the-art technologies and keep our customers on the Moore's Law curve. And this graph on the right shows for our data acquisition products how we continually lowered the price to keep up with the decreasing price of A to D converters over the years. So the customers who were using our data acquisition systems got a better price performance every year and didn't have to do their own custom board design to get that benefit. And one nice thing is that more and more of the customization over time moves into the software domain. And so we are taking the same approach for the embedded system market. The philosophy is we need to provide a wide range of different targets that have different mechanical form factors, that have different specifications and ratings, the latest chipset for the processor, for the FPGA and so on. And this becomes an alternative to having to do full custom layouts as long as we have something in the right mechanical form factor and with the right specifications. And the software tools enable you to move your code between any of the targets with little effort. The second problem with embedded design is the increasing design complexity. How do we deal with this increasing complexity? Well, really, the sophistication of the tools needs to increase to help people with this. We just can't manually do the same things we used to do. We just can't go do that kind of thing anymore. There are too many transistors, there is too much complexity, and the problems we need to focus on are really different. They are system level problems, they are non-linear, they are multi-domain. So what we really need to do is automate the work, and that's what these system level tools are about. Graphical system design is using high-level software tools to help automate the embedded software design process. And as you can see, graphical system design provides the most abstraction with increasing system complexity. Another problem is, even though FPGAs are ideal for digital control and have nanosecond timing and also have higher performance, but they are also a lot more complex to program, especially the I/O interface development, which is typically about 70% of the software development costs. But the real value lies in the control algorithms and signal processing running on the system. Our goal is to enable clean tech companies to focus the majority of their engineering dollars on high value tasks that give them a competitive advantage in the market. So what we are trying to do is create tools that automate a lot of those low value processes. You can see for a simple digital counter like this, the VHDL code isn't that bad. I'm reading from just a simple digital input-output buffer on the FPGA, and I can implement that in VHDL pretty readily. However, when I go to reading an A to D converter, now I have an SPI communication between the chips, and the code becomes a lot more complex. But you notice in the graphical code, it doesn't necessarily become more complex. And that's what we mean by automating the engineering and skipping a lot of the low-level development. But now, when we are talking about streaming data between the FPGA and the processor, there is something called DMA or direct memory access. Now we are talking about 66 pages of VHDL code. The goal with the graphical programming tools is that you don't have to write 66 pages of code. You should be able to just drop down another block and that's all done for you. Notice that the LabVIEW FPGA code has not grown more complex, and a graphical system design toolchain can help you automate a lot of engineering work. Fortunately, this has been the philosophy for the LabVIEW toolchain from the beginning, and actually FPGAs help with this a lot because actually truly parallel in hardware. So you can implement, for example, the space vector control along with the PID and notch filter, and it maps efficiently to the target and runs in parallel on the FPGA hardware with this kind of high-level programming. And we are able to take advantage of the parallel processing performance of the target. To learn more, download tools and example code and discuss your applications with other developers. You can join the community that is linked below. It has always been our mission to empower engineers in emerging countries to achieve sustainable prosperity. We are thus committed to providing increased access to NI technology. As such, if you are located at any of the above countries, you may wish to contact your local representative and see if you are eligible for direct support. We have been working with local incubators and collaborating with public sector partners as well. We hope to be able to nurture local innovators in your country. Thank you once again for joining me. I hope you enjoyed the session and learned something new from it. Do share your thoughts on this, and if you have any further queries, please do feel free to type in our Q&A window. Thank you.